In the absence of actual data for delta H and delta S, as long as we know the signs of those quantities, we should be able to make some predictions for the spontaneity of a reaction. We will still use the relationship for delta G. First, we need to look for the signs of delta H and delta S. Although we cannot get the sign of delta H from a balanced equation, we need to be told whether a reaction is exothermic or endothermic. We can get the sign of delta S. Remember, T is always positive. Second, since we're taking one term minus the other, we need to look to see which is bigger, delta H or T delta S. You might ask, how do we know which term is bigger if we don't have any numbers? Well, we can't. But here's what we can say. Delta H is usually hundreds or thousands of times bigger than delta S. But we're not comparing delta H and delta S. We're comparing delta H to T times delta S. Now we're going to assume that delta H and delta S stay constant as temperature is changed. You might explore that assumption in a later chemistry course. But for us, as temperature changes, delta H stays constant, but T times delta S will increase as temperature increases. Now, at relatively low temperatures, T times delta S is the smaller term. But as temperature increases, eventually we get to a temperature where they're equal. And as temperature continues to increase, T times delta S is the larger of the two terms. So again, this is temperature dependent. At low temperatures, T times delta S is the smaller term, whereas at higher temperatures, T times delta S is the larger term. So we define two temperature regimes. When we talk of low temperature, we mean temperatures where T delta S is the smaller term. The high temperature regime is where T delta S is the bigger term. Don't be confused by those labels. Low temperature and high temperature does not mean hot and cold to us. It has to do with how much bigger delta H is than delta S. If it's 300 times bigger, then the border between low and high temperature is at 300 Kelvin. If delta H is 1,000 times bigger, then the border between low and high temperature is 1,000 Kelvin. Since the actual values of delta H and delta S are different for each reaction, the border is at a different temperature for each reaction. Let's look at some examples to see how this works. In the first reaction, sodium reacts with water to form aqueous sodium hydroxide and hydrogen gas. If you have seen sodium react with water, you might guess that the reaction is exothermic. However, we can't tell simply from the balanced equation, so that information has to be given. So we know that delta H is negative. During the reaction, a solid and a liquid produce a solution in a gas. This would be an increase in the entropy, and the sign of delta S would be positive. So when you take a negative minus a positive, the result is always negative. That means that it doesn't matter which term is bigger, delta H or T delta S. This reaction is spontaneous at all temperatures. In the second example, dinitrogen gas reacts with dioxygen gas to form nitrogen dioxide gas. Though we can't tell by looking at the balanced equation, we are told that this reaction is endothermic, so delta H is positive. There is no change in state, but we see that 3 moles of gas goes to 2 moles of gas. This is a decrease in entropy, so the sign of delta S is negative. A positive minus a negative is always positive, so this reaction is non-spontaneous at all temperatures. As an editorial comment, it's a good thing that this reaction is non-spontaneous, since our atmosphere is mostly nitrogen and oxygen, and nitrogen dioxide is a toxic gas. So why are we making a big deal about the temperature? Let's look at this example. Dinitrogen tetroxide goes to 2 moles of nitrogen dioxide. Since the reaction is endothermic, the sign of delta H is positive. 1 mole of gas goes to 2 moles of gas, so entropy increases and delta S is positive. Now when we take delta H minus T delta S, it does depend on which term is larger. At low temperature, T is small, and T delta S is the smaller term. In that case, there would be a positive minus a smaller positive, which is positive. So at low temperature, this reaction is non-spontaneous. At high temperature, the situation is reversed. T is large, so T delta S is the larger term. A positive minus a larger positive is negative. At high temperature, this reaction is spontaneous. Our final example is a reaction we saw before when we first started talking about spontaneity. Dihydrogen reacts with dioxygen to form water in a reaction that certainly appeared exothermic. The sign of delta H is negative. In this reaction, 3 moles of gas goes to form 2 moles of gas, so delta S is also negative. With this combination, the result again depends on T. At low temperature, T is small, and T delta S is small again. So when you have a negative minus a smaller negative, the result will be negative. So at low temperature, this reaction is spontaneous. At high temperature, T is large and T delta S is the larger term. A negative minus a larger negative is positive. This reaction is non-spontaneous at high temperature. This is a curious result because the explosion of the hydrogen balloon certainly seemed spontaneous. But remember that the border between low and high temperature is different for each reaction. This reaction, that started at room temperature and then heated up rapidly, must have been at low temperature. But this result suggests that if the reaction gets hot enough, its spontaneity may be reversed. Clearly, the temperature inside the balloon was at what we would call low temperature.